We resume with our discussion of the simple pendulum problem, in which, recall, the Hamiltonian h of theta comma p theta was p theta squared over 2ml squared plus the potential energy, which is mgl into 1 minus cos theta, and we were specifically interested in finding out what the nature of the solution was as a function of time on the separatrix, which took you, for instance, from the saddle point at minus pi to the saddle point at plus pi in this fashion and back in this fashion, and of course you had small oscillations, larger amplitude oscillations inside, and this picture got repeated as you went along. We were interested in finding out what the explicit solution was on this trajectory here. On that particular trajectory, the energy had its value twice mgl, which is the maximum value of the potential energy, and we also saw that theta dot is proportional to cos theta over 2 on that trajectory. We saw this last time, and all you need to do is to integrate this. So this gives sec theta over 2 d theta is proportional to dt, and what is the integral of this? This leads to something like log tan theta plus pi over 4, and that is proportional to t on this side, apart from some constants. Therefore theta can be written down explicitly in terms of tan inverse of the exponential of some time. If you sketch that solution as a function of t, then you discover that on that solution theta of 0, we took this to be equal to 0, theta of infinity was equal to pi, theta of minus infinity was equal to minus pi. It starts at this point and ends at that point, and we assume that it passes through theta equal to 0 at t equal to 0, and the solution looks like theta t here versus theta. It started at minus pi, passed through 0 and hit plus pi in this fashion. So it behaved like a kink, as if it had a kink, and if you compute the angular velocity corresponding to the same solution, here is t, here is theta dot, the angular velocity, this quantity is by and large 0, except it takes a sharp peak up here and then back to saturation value, and therefore it looks a little bit like that in this fashion, and this is like a lump. This quantity, this solution, is related to what is called the soliton solution of the pendulum equation, of the Sine-Gordon equation, and this kind of lump solution, something which is essentially quiescent, nothing happens and then suddenly there is a little blip up there and then back down there to quiescence. This kind of thing is a special kind of soliton. It is called an instanton, since it happens in time, but we are not going to get into this business right now, except to mention that phenomena like solitons are very characteristic of nonlinear equations, and the Sine-Gordon equation, as I mentioned, is a prototypical nonlinear equation which has a very large number of applications, and this is a very well known and famous solution of that equation. The point I want to make here is that in as simple a problem as the simple pendulum problem, it already makes its presence out here. Okay, now let us get back to our primary discussion, which was to understand what kind of phase space structure does an integrable Hamiltonian system have, and for this we go back all the way to a very simple 2 degree of freedom problem. So far we have discussed a few 1 degree of freedom problems. Now let us do something in 2 degrees of freedom, and we begin to see how things can get a little more complicated, and the model I have in mind is the 2-dimensional harmonic oscillator. You could imagine this to be two oscillators, simple harmonic oscillators at right angles to each other, which you are familiar with from elementary physics. I write down now the Hamiltonian, and since we have decided to call q and p the coordinates and momenta, so let me call this q1, q2, p1 and p2. This is equal to p1 squared over 2m, that is the kinetic energy of the first oscillator, plus 1/2 m omega 1 squared q1 squared, assuming the oscillator to have a mass m and a frequency omega 1, plus an identical expression over 2m plus 1/2 m omega 2 squared q2 squared for the second oscillator. This then is my Hamiltonian, and I have the characteristic, the typical Poisson bracket relations, namely q1 with q2 is 0, p1 with p2, q1 with p1 is 1, as is q2 with p2. So the one variables q1 and p1 have nothing to do with the two variables, they are completely independent dynamical variables. It is two uncoupled simple harmonic oscillators with in general different frequencies added together to form a 2 degree of freedom system in 4-dimensional phase space. The phase space is the space of the 4 variables q1, q2, p1, p2, each of which ranges from -infinity to infinity. So that is our set of the Hamiltonian of the system. What is the set of equations? Well, it is quite evident that they are just two decoupled oscillators, so we can write down the equations instantaneously. This is p1 over m and p1 dot equal to minus m omega 1 squared q1, and similarly for 2 with the subscript 2 replacing 1, so q2 dot is p2 over m, p2 dot is minus m q2. And of course each of these oscillators, if you imagine them to be at right angles to each other, oscillates maybe in a plane, the q1 q2 plane, completely orthogonal to each other. So the problem as it stands is completely integrable, it is solvable. Now let us apply the general results that we know to this case and ask whether we can say something about the nature of the phase space and what kind of motion we really have. We need for its integrability, since in this problem little n is equal to 2, the number of degrees of freedom, we need 2 functionally independent analytic constants of the motion. And of course it is not very hard to see that this combination here, which represents the energy of the first oscillator, is a constant of the motion, as is this combination here. And since the 1s and 2s have nothing to do with each other, this and that are in involution with each other. So you could in fact call this f1 and this f2, and f1 comma f2, the Poisson bracket, vanishes, and each of these is a nice analytic function of the arguments, and therefore by the Liouville-Arnold theorem this system is integrable completely. We can write its solutions down explicitly. So let us formalize this. We have n equal to 2, and we could take f1 to be equal to p1 squared over 2m plus 1/2 m omega 1 squared q1 squared. In fact we could write fi is pi I and I equal to 1 or 2. We are guaranteed that f1 comma f2 is 0. Hence the system is integrable completely. Now we ask, what are the constants, what other constants of the motion could this system have? It is evident that the phase trajectories cannot be drawn by me since it requires 4-dimensional space, but we could draw the trajectories as projections of the trajectories into various subspaces. So for instance, if I try to draw the projection of the phase trajectory in the q1 p1 plane, for example, since it has nothing to do with this oscillator, it would just correspond to f1 equal to constant, which are ellipses as we know. therefore you get phase trajectories of this kind. And similarly in the Q2 T2 space you get ellipses of this kind. The periodicity here is 2 pi over omega 1 and 2 pi over omega 2 there. What would happen if we tried to project a trajectory onto the Q1 Q2 plane? What would you get? What would you get in general? Well, it is evident that Q1 for given initial conditions, it is clear that Q1 stays within this range and Q2 stays within that range. So the motion is restricted to some kind of rectangle, this being the amplitude in the first oscillator and this being the amplitude of the second oscillator. But is the representative point, is the projection of this trajectory, is it going to be a closed curve or is it going to be an open curve? It is certainly bounded, it is not going to go out of this region, but is it going to be closed or is it going to be open? It depends, absolutely right, it depends on the ratio of omega 1 to omega 2. If the ratio is rational, this means that the two periods are commensurate with each other, one of them is a rational multiple of the other, then it is clear the overall motion is periodic and the system given enough time will come back to its original point. Yes? In general you get Lissajous figures. Now the question is the Lissajous figure going to close on itself or is it going to be completely open? You are familiar from elementary physics with, for instance, depending on what the initial phase difference is between the oscillators, you would perhaps get pictures like this. You could get something like this, or you would get something like this, or you would get a pattern which fills up the space and never comes back to itself, depending on what the frequency ratio is. So it is clear, and we know this from elementary physics, that if omega 1 over omega 2 is rational, implies periodic motion. In other words, if we have two integers, say L and M, I don't want to use M because I have already used that for the mass, say K and L, such that K times omega 1 plus L times omega 2 equal to 0, it implies that the ratio is rational where K and L are integers, and then it is quite clear that the overall motion is periodic. But if no such relation exists with K and L being integers, then this ratio is irrational in general and the motion is not periodic. Although it continues to be periodic for the first oscillator and for this subsystem separately, we are now interested in whether the motion is periodic for the entire system or not. In other words, in the 4-dimensional phase space, does the point, representative point, come back to its original point position? And the answer is no, not if the frequency ratio is incommensurate. If it is irrational, the motion is not periodic. Such motion, where the actual motion is made up of two or more mutually incommensurate time periods, is called quasi-periodic, and the motion in general is quasi-periodic in this case. So let me write this down. What can we say about the motion in this case? Well, here is where the general theorem I talked about helps us. The motion has to occur on a surface on which H is constant, since the total energy is constant. It is a Hamiltonian autonomous system. It also has to appear on a surface on which F1 is constant and on a surface on which F2 is constant simultaneously. And of course the Hamiltonian in this trivial case is just the sum of F1 and F2, it is not functionally independent of F1 and F2. We have just two functionally independent constants of the motion. which are isolating integrals, namely f1 and f2. If we now go to action angle variables, and there is a standard method for finding the action variable in this case, it turns out that this Hamiltonian which we have written down here could be written in terms of action angle variables as follows. This Hamiltonian becomes I1 omega 1 plus I2 omega 2, where the two action variables I1 for example is an integral over P1 dq1 over a complete cycle. If the oscillator starts at the point say A and moves to B in the first oscillator, then it is an integral twice the integral from A to B of P dq, the corresponding P dq. So it is an integral over the orbit that I mentioned in the projection in the q1 q2 plane, and similarly for I2, and if you use those as your variables, and they can be shown to be canonical variables, then the Hamiltonian, this is what I call k of I, as promised does not depend on the angle variables but only on the action variables, and it is linear in the two action variables. You can easily check that the dimensionality is right, because action has the dimensions of energy multiplied by time and the frequency is inverse time. So the product of the two is has the dimensionality of energy. No angle variables are present here, and indeed you can see that in this simple case delta k over delta I sub I is in fact omega I, and the frequencies are independent of the amplitude of the motion because the Hamiltonian expressed in the action variables is linear in the action variables. Therefore when you differentiate it, there is no further dependence on the energy. We could therefore now go to a representation of the phase space in terms of the action angle variables themselves, and then what does it look like? Well, I know I1 is constant and I know I2 is constant, and this is the combination I1. This is like an ellipse in the q1 p1 plane, and an ellipse apart from units is topologically equivalent to a circle of some kind, and similarly in the q2 p2 plane this is an ellipse, and it is this combination that remains constant. That is again like an ellipse which is again topologically equivalent to a circle. So I could in fact now identify what the angle variables are. Going back to P1 Q1, once I give you F1, in other words once I give you this ellipse, then the state of the system of the first oscillator is specified completely by specifying for instance what this angle is as the oscillator moves around, and similarly for the second oscillator. Therefore the state of the full system, once you give me F1 and F2 which depends on the initial conditions, is specified completely by specifying two angle variables, which in this problem can actually be identified with the phase of the oscillator in the q1 p1 and q2 p2 planes. What kind of space is spanned by two angles each of which runs from 0 to 2 pi, two independent angles? It is a two dimensional space. What would that space be? Well, a rectangle but with the ends identified, because 2 pi should be identified with 0 and the other 2 pi should be identified with 0. So he is completely right. It is like taking a square of length of side 2 pi this is a square of side 2 pi, so here 0 to 2 pi in the first angle variable theta 1 and 0 to 2 pi in the second angle theta 2, but I must identify that point with this and this point with this. I must further identify this point with that and this point with this. So I must take this piece of paper and roll it around and stick this, glue this onto that and glue that onto this. What happens if I just glue these two together, preserving the orientation? I get a cylinder. I take the cylinder and I preserve the orientation of the two ends and I glue them on and I get a torus. So this is how the torus structure appears in the action angle space. So this phase space is nothing but the surface of a toe torus in which I could measure theta 1 as the angle in this direction and theta 2 as the angle in the transverse direction, in the cross section of this torus. And any point on the surface of this two torus represents a state of this oscillator for prescribed initial conditions. In other words, the action variables, the size of the action variables is prescribed once and for all. Periodic motion would correspond to the following situation: as the representative point traverses in this direction a complete loop, it should do so an integer number of times in the other direction. That would be 1:2 or 1:3 or even 1:1, for instance. More generally, k times this period plus L times the other period, that they should be commensurate with each other. K times one period should be L times the other period. In other words, the frequency ratio should be rational. In that case, this representative point which wanders on the surface of this torus returns to its original point and the motion is periodic. If the motion is 1:2 or 1:3, this simply means if it goes around here once, maybe it goes around in the other direction twice or thrice. It is hard for me to draw this, and comes back to the original point. The trajectory therefore would not fill this torus up, it would just be a curve on this torus folding around a few times like this, and then it does this, and then it does this, etc., and eventually comes back to the original point. On the other hand, if the frequency ratio is irrational, then we are guaranteed that the representative point never comes back to its original value precisely, but does so arbitrarily close to the original value an infinite number of times. The motion becomes quasi periodic. One way to see this would be to ask, let us imagine this frequency to be unity, and then we ask, how often does this representative point come and hit a cross section in this direction? So I take a cross section of this torus and I ask, here is the circle which represents the cross section. I start at some point here, so I am here, meanwhile it is going around in the other direction. When it comes back somewhere else and hits this cross section at some other point. It comes back a second time, it hits somewhere else, and so on. The question is, does it come back to the original value ever, or does it keep filling up this circle completely? It again depends on the frequency ratio, and we can prove the following theorem quite rigorously. Given a circle of unit circumference, if I add at each time step, I add a rational number, you are guaranteed that wherever you start, that point will be returned to in a finite amount of time after a finite number of iterations. Every point on the circle, whatever be the initial condition, is going to be revisited over and over again. All points are periodic points and the motion is periodic. On the other hand, if the number you add is irrational, modulo 1, because you are on a circle, then one can show rigorously that no starting point is going to be revisited. There are no periodic orbits at all. In fact, you can go further. You can show that the iterates of any starting point are going to eventually densely fill up this entire circle, and uniformly so. So it is not only important that it fills it up densely, but uniformly. There is no bias, there is no particular part of phase space which is preferred over other parts of phase space on this torus. So the iterates, the trajectory, any trajectory which starts here, will wind around this tightly till eventually it densely fills up. It is like a space filling curve. It densely fills up the torus, but never comes back and closes on itself. Comes arbitrarily close to its initial point many times, an infinite number of times, but never recurs, and the motion is quasi periodic. So this is characteristic of quasi periodic motion, that the system densely fills up a certain subspace of the phase space, and it is said to be ergodic on this torus. So quasi periodicity implies, to use a technical term, ergodicity on the torus. I repeat, by ergodic I mean that any set of initial conditions, I take a little patch of initial conditions here, as time goes on each of the points in this patch evolves in time, wanders around this torus, this little patch visits every neighborhood of this on this torus an infinite number of times, comes arbitrarily close to every starting point and eventually fills up this entire torus uniformly and densely with no exceptions. It is said to be ergodic on the torus. What that implies is, if you want to compute long time averages of any physical quantity, you can replace the long time average by a statistical average with a uniform measure on this torus, a uniform probability distribution on this torus, and that is the implication of what this word ergodicity means. And in fact, you know that in statistical mechanics you normally replace time averages by ensemble averages, by statistical averages, and the distribution function has to be prescribed to you by the conditions under which the system is kept, and that implies a certain kind of ergodicity. It assumes that time averages can be replaced by statistical averages. And this is exactly what happens here in this dynamical system, which displays quasi periodicity here. We can go further. Our phase space is 4 dimensional. Any motion for given initial conditions is restricted to a 3 dimensional subspace of this 4 dimensional space, namely the energy surface. Now in a 3 dimensional space, the motion is further restricted in each case to a 2 dimensional surface, namely some kind of torus, and it is evident if I try to draw this, for instance, perhaps there is a torus here, and if I draw a cross section of it, it is like this. A different initial condition would correspond to a different torus of this kind, it would be like that, for instance, schematically. So the whole space, the energy surface, is simply filled up by these successive nested tori, and moreover, since phase trajectories cannot cross themselves, it is evident that if you start on one torus, you are never going to escape, you are going to be on that torus. If you start on a different torus, you remain on that torus. The gaps between these tori are also filled up completely by other tori, and that is the structure of the phase space for an integrable system like a 2 dimensional harmonic oscillator. But the matter is more general than that. Even more generally than this, if you have a 2 degree of freedom system which is completely integrable, then the motion in general is restricted always to some 2 dimensional torus. What would be the major difference between an arbitrary 2 degree of freedom integrable system with bounded motion and a harmonic oscillator? What is special about the harmonic oscillator? What is the feature that is absolutely special about the harmonic oscillator? You can't jump between tori, but that is true even for a nonlinear system, even in general this would be true, and that is simply a consequence of the fact that once you are on a torus, that represents a constant of the motion and you are on that surface. What is very special about the harmonic oscillator? What the fact that the cross section is a circle, we are talking about topological aspects here, so the fact that the cross section is a circle instead of an ellipse and so on, this makes no difference, that is simply choice of units. What is particularly special about the harmonic oscillator? The equations of motion are linear, that is certainly true, it is not a nonlinear system, but what is very special about it? Go back and recall that omega I was in general equal to delta k of I over delta I sub I. What happened in the case of a harmonic oscillator? It was constant, the frequencies were constant, independent of the initial conditions, independent of the energy of the oscillator, independent of the amplitude of oscillation. This feature is not true in general. In general, this is some function, this is equal to some function of all the action variables, and that would mean that the frequencies on the different tori would be different in general. It also immediately implies that if you have a nonlinear system of that kind, on certain tori, depending on what the values of the action variables were, because that is what determines the frequencies, frequency ratios could become commensurate, but you move to another torus, it could become incommensurate in general. So the motion could be actually periodic on some tori and aperiodic, quasi periodic on other tori. Generically, of course, it would be quasi periodic, but there could be accidental cases where you have resonances and the motion reduces to periodic motion on some tori. That is indeed what happens. What happens further is even more interesting. In a general 2 degree of freedom system, if the system starts out as integrable and you add to the Hamiltonian a small piece which takes you away from integrability and you lose the integrability property, then what happens is even more interesting. In general, this set of tori would no longer exist because it is no longer an integrable system, but in general it does not happen globally. In other words, first for certain sets of initial conditions, for certain delicately balanced frequency ratios, the tori get destroyed, the rational tori get destroyed first, and gaps form between tori, and in those gaps the motion actually becomes irregular. It is no longer periodic or quasi periodic, it becomes chaotic, and this happens when you have not an integrable system, but to an integrable system you add a small perturbation which destroys the property of integrability, and then typically you have chaotic behavior in the gaps between these tori. As you jack up the strength of this perturbation and make it go further and further away from an integrable system, in other words certain symmetries are destroyed more and more, then successive tori go on getting destroyed and still certain tori persist on which the frequency ratio is quote unquote extremely irrational. So now we are getting into number theoretic considerations, and we have to discuss, we have to decide what is meant by a number being more irrational than another number. We will come to that in a second, and eventually all the tori get destroyed and the motion becomes completely chaotic, and we will talk about chaotic motion in much greater detail a little later, but this is the mechanism by which, this is a rough idea of what happens in such systems. In the same breath, let me mention that if you took an n degree of freedom system, for example n harmonic oscillators independent of each other, what would the motion be on? Well, the individual energies of these oscillators are n constants of the motion in involution with each other, so the system is integrable in the same sense. What would then decide where this representative point is? Just the angle variables, the individual phase angles of all the oscillators in the corresponding QP spaces. What would you represent that kind of phase space by? By an n torus, the generalization of a 2 torus to n dimensions, in which n angles would specify the state of the system, and then you could ask, is the motion quasi periodic on this n torus or is it periodic, and in general of course the answer is it would be quasi periodic, unless you had n minus 1 relations of the form k1 omega 1 plus L1 omega 2 plus etc. up to something times omega n equal to 0, and you had n minus 1 such relations between the frequencies. If you did, then all the frequency ratios are commensurate with each other and you have periodic motion. But if even one of them is lost and you do not have that relation, then you have some degree of quasi periodicity, and if you have no such relation at all with integer values of these parameters here, then the motion is completely quasi periodic on an n torus. I cannot draw a picture of an n torus. What I have done here is to draw a section of a 2 torus, and that is the best I can do on the blackboard, but you can easily conceive of the fact that you have motion on an n torus if the system is integrable. The phase space dimensionality is 2n, the energy surface dimensionality is 2n minus 1, and the torus is an n dimensional object. Now in 3-dimensional space, it is clear that 2-dimensional objects such as these rubber tubes, they striate the entire space. You can put one inside the other and fill up this entire space. if you had, instead of 3 dimensions, if you had 4 dimensional space and you took these 2 dimensional objects here, they clearly do not fill up the space. There is no way in which the entire space is laminated by them. So it is evident immediately that if you took 3 or more degrees of freedom, n greater than or equal to 3, the phase space is 2n dimensional. The energy surface is 2n minus 1 dimensional. If the system is integrable, the motion occurs on an n torus in certain variables, and this is n dimensional. If n is 3, then this is a 3 dimensional object, this is a 5 dimensional object. The difference in dimensionality is 2, not 1. So it is clear 2 3 dimensional objects cannot separate this 5 dimensional space. Or to put it another way, in 3 dimensional space, if I have a 2 dimensional surface of this kind, a torus, there is an inside and an outside. It splits up this whole space into an inside and an outside. That is not possible if the dimensionality between the object you are considering and the dimensionality of the space is greater than 1. Is this clear? If I take 3 dimensional space and I draw an infinite plane in it, that is a 2 dimensional object, there is an up and a down, it splits this space into 2 parts. But if I took a straight line, which is a 1 dimensional object, it does not split 3 dimensional space into 2 parts at all. In exactly the same way, a 2n minus 1 dimensional energy surface cannot be split up into disjoint parts by n dimensional objects if n is greater than or equal to 3. When n is 2, this happens, because this is 2 and that is 3, and that is exactly the situation we looked at there. The implication is deep. The implication is these gaps here would all be connected to each other. There is no way you can have an inside and an outside unambiguously. All such gaps, you must imagine, would be connected to each other. There is enough room to go from one gap to another gap. And I already mentioned that once you have a perturbation which destroys integrability, then some tori get destroyed and part of the motion for some initial conditions becomes chaotic. But if the motion is chaotic in this region and this region is connected to all the other chaotic regions, this means that the chaos can spread. That all random motion, all chaotic motion in non-integrable Hamiltonian systems with 3 or more degrees of freedom, all such regions of chaotic motion are in general connected to each other, and they form what is called a stochastic web, and a kind of diffusion will occur over long time periods from one region to another, and this has profound implications in dynamical systems, especially in applications such as accelerator physics. This immediately makes a huge difference, because it's, in some sense it says that regions where the dynamics is unstable, exponentially so, are actually spread out all over the phase space, not confined to certain regions of it. We will try to come back when we talk about chaos, we will come back to some implications, but the reason I digressed here was simply to point out that very simple arguments based on dimensionality can actually lead us to these conclusions, fairly wide general conclusions in this case. So having talked a little bit about quasi-periodicity, let's now take up a specific example. We go back a little bit and take up a 1 degree of freedom system where I show you explicitly how the nonlinearity plays a role and how time periods could actually depend, for instance, on the amplitude and the energy. And let us try to see if we can generalize the harmonic oscillator. So let us look once again at a 1 dimensional 1D nonlinear oscillator. I have a single degree of freedom, let us call it Q, and a conjugate momentum P, and the Hamiltonian in this case is H of Q and P, and this is equal to 1 half, let us write this as P squared over 2m plus a potential energy, let us fix the frequency of this oscillator, the natural frequency or some constant to be equal to 1. So in suitable dimensions this thing here becomes q to a power which is not 2, this is 2 would mean a harmonic oscillator, a linear harmonic oscillator, but let us in general have a power 2r for instance, and let us set the mass to be equal to 1, so we just have this as the Hamiltonian divided by 2r. To start with, let us say r is a positive integer. So r equal to 1 implies simple harmonic oscillator, the linear harmonic oscillator. Well, we could write the equations of motion down immediately, and what would they be? As before, q dot is p over m and p dot is minus delta h over delta q, so this would be equal to minus 2r cancels, so q to the 2r minus 1. If r is greater than 1, it is clear this is a nonlinear system and a badly nonlinear one, because if r is 2 for example, this is already a q cube term and you can't linearize about the origin. Where are the critical points? The origin is the only critical point, so Cp at 0 0. What does the linear matrix say? If you linearize this, what would this be? This would become, this becomes 0 right here, and then what would happen here? You would get a matrix, a linear matrix. If I tried linearizing, I would get L equal to 0 1 over, oh let us just take this to be 1 since I have chosen units such that the mass is 1. So this is 0, this is 1, and out here I get 0 and 0 because this is already a higher order term for r greater than 1. What would you say are the eigenvalues of that? 0 and 0, any triangular matrix the eigenvalues sit on the diagonals. So this is in fact a degenerate case. We are not able to decide if the origin is a center or if it is some other kind of critical point based on linearization, simply because the system is degenerate, the critical point is degenerate. But let us take recourse to physics and ask what kind of system we have, and then I will point out a method by which we can decide that the origin is in fact a stable center, and we can do that very trivially in this problem by simply drawing the phase trajectories q versus p. Yeah. Yes, I am taking a special case by, the question is why am I restricting myself to r equal to a positive integer? I am going to relax this condition subsequently. So let us first take r equal to a positive integer, see what happens, draw some conclusions, and then we relax this condition, see what happens. Okay. What kind of phase trajectories do you get for this system? The way I have written it, it is clear that whatever phase trajectory I get, they are closed curves for all positive E, because these are all positive terms, each of these. It is completely symmetric about the q axis as well as the p axis. The motion is evidently restricted to some kind of rectangle, so we are going to get some kind of oval, this being the amplitude of the motion. When r is 1, of course it becomes an ellipse. When r is equal to 2, then you get p squared plus q4 equal to a constant, and that is a sort of squashed oval. By the way, what do you think will happen if r becomes larger and larger? What do you think will happen to this curve? We are plotting a curve, we are plotting a graph of this quantity equal to some constant E which is positive, and what happens to this graph as r becomes larger and larger? In which direction is it going to get squashed? What is going to happen? It's evident that this amplitude restricts the total energy restricts this amplitude. This amplitude in fact is given by, if this is A, then it is quite clear that A to the 2r over r, 2r is in fact the energy. because the kinetic energy is 0 at these points. So what kind of graph would you get if r becomes larger and larger? I fix the energy and then I just change r, what happens? Would this ellipse become fatter like that, or would it become thinner in this fashion? What would it do? Yeah, it's clear. No, I fix the amplitude, I fix this, I fix the energy, and then ask what does this graph look like? I fix the amplitude and ask what does this look like?
You are talking about a particular set of initial conditions, right?
I am talking about, okay, let me be specific. I fix the amplitude and now I ask, I change this r, I increase it. I do the same problem for a different r. As r increases, what happens to this graph? It will do this, it will start doing this. As r increases, it will do this. Eventually as r tends to infinity, it would become the rectangle. Suppose r, we will take what he said a little seriously now, suppose r becomes smaller and smaller. If r is equal to 1, what would happen? Then of course you could say this term changes sign. If r becomes less than 1, for example, this term changes sign. We want to keep everything positive, so let us take modulus q to the 2r. What happens if r is equal to 1? It is just an ellipse. What happens if r is equal to a half? It is not a parabola. So let us go back, let us do a little bit of elementary calculus. I asked the question, x over a to the power r plus y over b to the power r is equal to 1, and I want to plot this on the xy plane. What does this graph look like? A and b are some positive numbers. Since these are positive numbers, it is quite clear that the motion is restricted to some kind of rectangle of this kind. This is size a and this is b. When r is 2, this is an ellipse. So let me draw that. What if r is equal to 1? What kind of straight line? These are moduli. Absolutely, so it would be some curve like this. This is r equal to 1. What if r is equal to 4? It would get fatter and fatter, it would start doing this. And finally, this rectangle is the limiting case when r tends to infinity. What happens if r becomes less than 1? Yeah, absolutely, the curve starts getting concave, it starts doing this. So this would correspond to r less than 1. What happens if r tends to 0? Well, as r tends to 0, either x is equal to a and you are finished, or y is equal to b and you are finished, and the other variable must be 0. So it would be the axes themselves. It would be the axes themselves. So it would tend to this. So it is really a whole family of graphs that we are talking about here. The ellipse is just one such member of this family. So coming back to what we were doing, here is q and p on this side. The phase trajectories are some kind of ovals, completely symmetrical in this fashion, and for every set of initial conditions you have a concentric oval of some kind, and these are the phase trajectories. A very nonlinear oscillator, and of course the system is integrable as it stands, simply because there is a constant of the motion, just the Hamiltonian itself in 1 degree of freedom, that suffices. It is some algebraic function of p and q, and that is a constant. The motion is bounded, it is periodic motion, it is completely clear. What can we say about the time period of motion? How does it depend on the energy? How would we determine this? Of course, in the case r is equal to 1, the simple harmonic oscillator case, we could solve for p and q explicitly because the equations of motion were linear and you got trigonometric functions and we know the time period of trigonometric functions, we know the periodicity. But what happens if it is non-linear? What for instance would happen if r is equal to 2 or 3 or 4, what would happen? How would you determine the time period of this oscillator? Specifically I would like to know how it depends on the energy of oscillation, on the total energy. What would one do in such a case? Well, you agree that the time period of motion by symmetry is 4 times the time it takes to go from there to there, and by symmetry it is just 4 times the time taken to go from here to here, or the oscillator to start at the origin and go to the end of its amplitude. So suppose the amplitude is A and I look at this portion of the trajectory and I write the time period as equal to over the full orbit dt 0 to t dt, but I could write this as equal to 0 to a dq over dt, which is q dot, but I must make sure about the sign of this quantity, which could either be plus or minus. It is positive in the upper half part of the diagram and negative here, and by symmetry, since we said it takes the same time to go from here to there as from there to here, this is equal to 4 times on this set to go from here to there, to go from 0 to the amplitude A, where by q dot I mean the positive square root of E minus this quantity apart from some constant factor. So this is proportional to, apart from some constants, numerical constants, it is proportional to 0 to a dq divided by q dot, but q dot squared, p squared by the way is just the same as q dot squared, since I have set the mass equal to 1, is E minus q to the power 2r. So this is square root of E minus q to the power 2r apart from numerical constants 2r over 2r. But what is E for a given amplitude A? A to the 2r over 2r. So it is evident that this whole thing, keeping all factors of A present apart from some numerical constants, this goes like integral 0 to a dq over square root of a to the 2r minus q to the 2r. How are we going to evaluate this? For general positive integer r, this is not easy to evaluate, it is some complicated integral. You can't write this in simple form by any trigonometric substitution as you could in the case when r was equal to 1. Then of course you got a sine inverse and you could do the integral, but we do not need to do that. We need to only extract the dependence on the amplitude A. What should I do to extract this dependence? I could expand it binomially, integrate term by term and then reconstitute the whole thing, but there is a much simpler method by which you can extract the entire A dependence of t in one shot. Q is bounded between 0 and A, so what does that suggest to you? Well, the only length scale in the problem is A, we would like to know how t depends on A. So I should scale out this quantity A, so I put Q equal to AU, a change variable of integration, and then this implies that t is proportional to an integral from 0 to 1, a numerical integral dq, that gives me a factor a du divided by, I get an a to the 2r here which comes out of the square root and gives me an a to the power r. So a to the power r square root of 1 minus u to the power 2r. Multiplied by a numerical factor, that integral is guaranteed to be some finite number because the only singularity which you have is at u equal to 1, and for instance if you had u to the power 4 here, then you have to worry about whether this integral exists or not, but you have 0 to 1 square root of du divided by square root of 1 minus u to the power 4, and that is an integrable singularity. Let me show you why. For instance, if you had 0 to 1 du over square root of 1 minus u squared, this of course could be written as 1 minus u times 1 plus u, and then you immediately see that this is the part that causes trouble at 1, not this is quite finite, and this is like dx over square root of x. When you integrate, the square root of x goes on top and the contribution at the upper limit vanishes. If you have a higher power like 1 minus u to the power 4 for instance, then that could be written as 1 minus u squared times 1 plus u squared, and once again it is only square root of 1 minus u that creates a problem, and this is true for every positive integer r. So the integral is actually finite, there is no difficulty at all, and it is some gamma function, it can be written down in terms of Euler gamma functions etc. But what we are interested in physically is the dependence of the time period on the amplitude, and that is like 1 over a to the r minus 1. What happens when r is 1? It is independent of the amplitude, that is exactly what the harmonic oscillator is, but for all other r there is a dependence on r, on this index r. In fact, if you set r is equal to 2 and we have an oscillator which is a quartic oscillator, you have the Hamiltonian as p squared over 2 plus 1/4 q to the power 4. The time period of oscillation in this oscillator is proportional to 1 over the amplitude. In other words, the smaller the amplitude, the longer the time period. It seems counterintuitive, but why is it happening? Why is this happening? Why is the amplitude increasing as the amplitude decreases? And in fact, as the amplitude goes to 0, the time period is going to infinity. What is the reason this is happening? What is the shape of this potential energy? It is very flat at the origin, absolutely right. So if I plot V of q versus q, this potential has a third order minimum here, it is extremely flat. So as you come smaller and smaller, as the total energy decreases, the restoring force becomes smaller and smaller because it is extremely flat here. If you started with this much as the total energy, then by the time it gets here it has quite a lot of kinetic energy and it zips right past, but if you start here it does not have enough kinetic energy to zip past this and it rolls down this extremely slowly, and because it is not a simple minimum of the potential, it is not parabolic at that point, you have a diverging time period as a function of the amplitude. This is characteristic of nonlinear behavior. In this case it is extremely flat, higher order minimum is immediately going to lead to such funny kinds of behavior. We are actually interested in finding out how the time period or the frequency changes as a function of the total energy of the system. How are we going to do that? We already have this result, t goes like 1 over a to the r minus 1. So how does it depend on the energy? Exactly, a to the power 2r is proportional to the energy, which implies that a is proportional to e to the power 1 over 2r, and that in turn implies that t goes like a to the power 1 minus r, which is a to the power 1 minus r over 2r, t e to the power 1 minus r over 2r. So that is the dependence on the energy of the time period. We could translate this to the frequency, and we will do this and see what the action variable is in this case, and we see how the tori actually depend, the size depends on the initial conditions in this case. So it is a very simple illustration of a nonlinear oscillator in which you have almost the same kind of structure as in the simple harmonic oscillator, but because it is nonlinear you have an actual dependence of the frequency of oscillation on the energy of the system. So let us stop here and then we take it from here.